With the discovery of these new particles came the discovery of some new physics. In particular, we got a whole bunch of new conservation laws. So we were already familiar with conservation of energy, conservation of momentum. There's also conservation of charge, which we haven't really covered, but that was something else. There's conservation of angular momentum, which is L. So we had a variety of conservation laws, but now we found some new ones because we couldn't explain exactly what was going on without adding some new conservation laws. For instance, in a reaction where you have a proton colliding with a neutron, we never saw two protons and an antiproton come out. Even though this doesn't violate any of our known conservation laws, you can get 3 particles from 2 as long as you convert some of the kinetic energy, so that's why they've got to be moving pretty fast, and you need particle accelerators and all of that. If you convert some of that kinetic energy to mass, because Einstein tells us energy and mass are convertible. So we didn't have any law that would tell us why this couldn't happen, until we proposed a new law called conservation of baryon number. Now, what the heck is baryon number? Well, it's pretty similar to nucleon number, which if you haven't had chemistry, you might not be familiar with that either. But protons and neutrons are nucleons, and if you've studied some nuclear reactions, you know that the number of nucleons you start with has to equal the number of nucleons you end with. You can switch back and forth between protons and neutrons, but the total number of n plus p has to remain constant. Well, we just kind of expand this because we now have some other particles that we call baryons, and if we count those together with the nucleons, then that number of particles has to remain constant. Now remember, with antiparticles, they have negative values, so negative charges if they have positive and vice versa. And if we're counting nucleon number or baryon number, then antiparticles get negative numbers. So let's look at this reaction right here. A proton has a baryon number of 1, and a neutron has a baryon number of 1. So that gives us a sum over here of 2, a baryon number of 2 to start with. Over here I've got 1 for the proton, 1 for that proton. This proton gives me negative 1, so the sum of these guys is going to give me 1 because those guys cancel out. So I can't go from a baryon number of 2 to a baryon number of 1. It violates conservation of baryon number. Now in order to fix this reaction, I could add another proton in here, a regular proton. And if that happens, I add another 1 here, which makes my baryon number 2. And this actually does happen, so we can get rid of the does not happen little hash mark there. So conservation of baryon number. Now what the heck is a baryon? There's a whole bunch of them. Here is a little sample. Protons and neutrons, as we already mentioned, are considered baryons. We also have a lambda particle, 3 different sigma particles, a positive and a negative one and a neutral one, Xi particles, omega particles, and some other particles. Here are their masses. You'll see they're all relatively close to the same mass for these particles. This here is their baryon number, so the regular particles these all have positive 1 baryon numbers. The antiparticles will have negative 1 baryon numbers. Now, this wasn't the only conservation law we came up with. We came up with another law called the conservation of lepton number. What the heck are these crazy words that Mr. Giusti is saying? Well, we had to come up with names for all these crazy things we were seeing. What's really crazy is these things exist, and when we slam particles together, all kinds of crazy things pop out. So there are only 6 leptons, so as opposed to that previous list where it was just a sample. Here, this is all there are, and really there's just kind of like 3: the electron, the muon, and the tau. And then there's a neutrino that goes with each of those particles. You'll notice these masses are not similar at all. The electron is got a relatively small mass, muon a couple hundred times bigger, tau a couple thousand times bigger, a few thousand. These neutrinos are pretty close to massless, but we think they have very small masses. If you look, this is in electron volts, not mega electron volts. So this is not close to the mass of the electron. It's like 1,000,000 times smaller. And in fact, we're not even sure. We know that the sum of the masses of all 3 neutrinos is not 0, but it could be that one has mass and the other 2 don't. We're not exactly sure. These are elusive squirrely particles that we'll talk more about later. It turns out to conserve lepton number, you actually conserve each, there's actually 3 different types of lepton numbers. There's the electron lepton number, muon lepton number, and tau lepton number. And in most situations, those lepton numbers are conserved separately. So I need to end up with with the same electron lepton number as I started with. So let's look at some examples of applying these ideas. So can these reactions happen? Well, I've got a muon here. So let's, in these first 3 interactions here, all we have are leptons. So let's sum the lepton numbers, the electron lepton number and the muon lepton number. You'll notice we don't have any taus here and we don't have any tau neutrinos. So the tau lepton numbers are going to be 0 for everything. So we're not going to worry about that. We're just going to look at the electron lepton number and the mu lepton number. Now this mu here, let's jump back, and we got to be careful to see if this is a regular particle or an antiparticle. The electron, we know the regular particle is negatively charged, but that's not always the case. Like the proton, the positively charged one is the regular particle and the negatively charged one is the antiparticle. So let's go back and check for the muon. The regular muon is the negatively charged one, so okay there. This is going to have a positive 1 muon lepton number, so that's the total over here because that's all we got. The electron lepton number starts out as 0. Over here I've got a positive 1 electron lepton number, and this is going to give me a negative 1 electron lepton number because this is an antineutrino. The bar over the top indicates that this is an antiparticle, and the E here indicates that this is an electron neutrino. So I've got 0 electron lepton number because these 2 guys cancel out, but I've got an issue here because I don't have any other particles and these guys don't have any muon lepton numbers, so I've got 0 here. So this cannot happen. No bueno, because it violates conservation of muon lepton number. Alright, this is the same thing over here, so we start with 0 and 1. Over here I've got this and that, and here I've got a regular muon neutrino, not an antineutrino, which is going to give me, so this is still going to sum to 0, and that is going to give me 1 muon lepton number. So this guy checks out, and this is a decay process that does happen. Alright, a couple more here. Again, 0 and 1, we're just starting with the same muon. We get our electron, and here I've got an electron neutrino, not an antineutrino, so that makes a positive 1. So I'm going to add these 2 together. I'm going to get a 2 here for my final electron lepton number and 0 here. So this one is doubly bad. It violates, the 2 doesn't match the 0 and the 0 doesn't match the 1. So we'll give it 2 strikes. This guy will definitely not happen. Okay, and just to look at something other than starting with a muon, here we start with a pion. Now a pion is neither a baryon nor a lepton, so it doesn't have, in these situations we should also look at baryon number because that is conserved, but none of these had baryons, so these were all 0 all the way, so that was fine. Okay, over here all of these are 0 for the pion. It's not a lepton or a baryon. Over here I have a positively charged muon, and remember the negatively charged one was the regular particle, so this is going to have a negative 1 muon lepton number. This guy is a muon neutrino, and it's a regular one, so it's going to be positive. So there's no electron leptons going on at all here, so that's 0. These guys cancel out and give me 0, and there's no baryons over here, so this guy also checks out as well. So these are the types of things you're going to be doing on your homework. It's a little tedious, but it kind of eventually gives you a feel for what is going on with all these conservation laws. So let's kind of take a look at where we're at with our collection of particles at this point. So in the last video, this is a typo there, that shouldn't be a G, that should be an S. Okay. So we have these particles up here that we call bosons, or more specifically gauge bosons, because there are other types of bosons that we'll see later. This is named for what's called gauge theory that predicted these things. Anyway, these are the force-carrying particles. They mediate the forces. So strong force gluons, electromagnetic force photons. The weak force is mediated by the W and Z bosons. W particles are also charged, so they feel the electromagnetic force. They aren't typically considered to mediate that force, but they do interact electromagnetically. Now, the other force we left off of here is the gravitational force mediated by the graviton, and that's because we haven't found it and we don't know too much about its properties. So here we can see the classes of particles, and we can see why they're organized into these classes, and it comes down to the forces that they feel. So charged particles, if we kind of zoom out from these subatomic particles, in general, anything with mass feels gravity. Anything with charge feels the electromagnetic force. So it's a similar idea. We're just kind of zooming in. Now we're saying anything that's a lepton feels the weak force, and if it's got charge, it also feels the electromagnetic force. Now the neutrinos are not charged, so they don't feel the electromagnetic force. Okay, we saw mesons in the previous video, particularly the pion, and those kind of get grouped together with these new things that we looked at called baryons in a category called hadrons. So the hadrons break apart into, well, you don't break them apart, but the hadron has subcategories of mesons and baryons, and those go together because they feel all of the forces, strong, electromagnetic, and weak. As long as they're charged, there are some neutral ones that won't feel the electromagnetic force. So here already we're getting a pretty complicated picture. This is sometimes referred to as the particle zoo, because once we started building accelerators and getting new particles, for a while they were just finding new particles almost every day. And there's a lot more than this too. We're going to get into some of them, not all of them, because there's hundreds and hundreds of particles that show up in these collisions. All right. So just to summarize a little bit, gauge bosons are the ones that mediate the forces. Leptons interact weakly, meaning they feel the weak force, and if charged electromagnetically, but they do not feel the strong force. Hadrons interact strongly and weakly. The strong force usually is the dominant force because it's strong, and if charged, they also interact magnetically, and we can divide them. We can divide the hadrons into baryons and mesons. Now, all three of these classes will feel, they all feel the gravitational force as long as they have mass. Now, the photons are massless, but even in some circumstances in general relativity, we would still say that they're affected by gravity. Now, these forces are also related to how stable particles are. Almost all of these particles, all these new particles, are unstable. They decay really quickly into other things. That's why we don't notice them in our regular labs. We have to have these high energy particle accelerators and really sensitive detectors to catch them before they go away. And depending on what force is the main force causing the decay or mediating the decay, we get different products out. We know that if we get leptons coming out, like electrons or neutrinos, that was the weak force involved there. If we've got photons coming out, then most likely that was the electromagnetic force. And strong force interactions produce, or decays produce, pions. Now these are kind of general rules of thumb, doesn't always hold true. But this is good evidence that that's the force involved in the decay. So let's look back at our big ugly chart here for a minute. So over here it's talking about the decay modes. Essentially that's what this particle breaks apart into, and there can be different modes. So let's take the W bosons. There's our typo again. If we take the W boson, it can break up into an electron and an electron neutrino. Or it can be a muon and a muon neutrino, or a tau and a tau neutrino. And so this is going to be mediated by the weak force, because these are all leptons here. The pion, at least the neutral pion, will become two photons. This gamma here is the symbol for photon, as shown up here. So this tells you that this decay was due to the electromagnetic force, whereas the kaon breaking down into pions is going to be mediated by the strong force. Alright, the last thing I wanted to look at was these neutrino things. We haven't talked about them too much yet, but they have an interesting history. They were actually discovered really early on, even though they were, or at least they were proposed really early on. They are really hard to detect because they don't interact with almost anything. They have almost no mass, but they are important. For instance, we saw early on that if you have a reaction like a neutron decaying into a proton and an electron, that the proton and the electron didn't actually fly apart in exactly opposite directions. So you might have had the proton going off this way and the electron going off that way at an angle. And the neutron's not there anymore. And so you can't have two particles. This violates conservation of momentum. You'd have to have a third particle going off in this direction, and it turns out that that was an electron neutrino. In this case, an anti-electron neutrino to conserve lepton number, because we created an electron lepton here, so we need an anti-electron lepton there. So we knew that some other particle had to exist, and it was actually Enrico Fermi, and he had a student, Eduardo Amaldi, who kind of came up with the name neutrino, which in Italian more or less means a little neutral one because it had almost no mass. Again, these things are pretty important because, well, for one thing, again, these things have all kinds of applications. One of them is kind of confirming the fact that a process called fusion is what powers the sun. Fusion gives off a bunch of neutrinos, so we should be able to detect those neutrinos here on Earth. In fact, there are trillions of neutrinos flying through your body every second coming from the sun. And even if it's nighttime, most of them fly right through the Earth, so even if you're on the other side of the Earth, there's still trillions of them flying through your body every second. And we have detectors to try to get some detections of neutrinos because it's really hard. So they tend to be really big and complex machines, often really far down underground. Sometimes they'll use mine shafts so they don't have to dig another hole. And the reason why they put them so far underground is most all other particles will be stopped by traveling through a couple miles of Earth. But neutrinos, they go right through, no problem. And so if we see interactions with these detectors, we can be pretty certain that it was a neutrino that caused that interaction. Some other interesting things about neutrinos is, we saw the three different flavors is what they're called. Why, I'm not sure. But they can change from one flavor to another, what we call oscillation. And this actually was a conundrum, a paradox with the neutrinos from the sun, because we knew that fusion should produce electron neutrinos, and the sun wasn't producing nearly enough electron neutrinos. But it turns out that they just changed to other types of neutrinos along the way. Now that is kind of confusing because it seems like it would violate the individual lepton numbers. In fact, it does. So we now know that they're not strictly conserved. In most interactions they are, but a free neutrino just flying through space can oscillate and change into a different neutrino and violate an individual lepton number. But we have never seen a situation where total lepton number is not conserved. So if you add up all three types of lepton numbers, that's still good. Some other implications of these oscillations are that it cannot have zero mass if it is allowed to change type. I'm sure it's some complicated explanation why, I'm not even sure the reason, but so there are other implications for these things. Alright, that's all I've got for today.